Oh, hello everyone. Okay, this video I'm going to talk about the kinematics, 1D kinematics, and this section is I will go to the instantaneous velocity. In a previous video, we show you the definition of average velocity and average speed, and then we go a little bit further. We go to the instantaneous velocity. And what's the instantaneous velocity? Is instantaneous velocity. In fact, it's very similar to average velocity. Okay, the average velocity, the definition is the displacement divided by time interval. Now, the instantaneous velocity, if the delta t is small, in mathematics, we use this expression. If delta t is very, very small and approach to zero, okay, let's call instantaneous velocity r. Sorry, I should move this a little bit. I should move this a little bit further. Okay, on the right hand side. And instantaneous velocity, the notation is v, in v. Okay, v. Okay, it's not like the average velocity. Average velocity, we have a bar over the v. Okay, that means average velocity. But instantaneous velocity, we don't have the bar over v, just write the v. Okay. And at the same time, I believe every one of you are learning the calculus. Actually, this is the definition of This is the definition of derivative, and its derivative is x doing the derivative with respect to t. Okay, so if we use the calculus language, it will become like this. It's dx over dt. Dx over dt. That's calculus language. Okay. And so what's the if and the dx over dt, if you know some mathematics, you know the derivative in calculus class, it will show you the physical meaning of derivative is slope. The physical meaning of derivative is slope. Is a slope. And so, and more specifically, is xt diagram. Okay. The instantaneous velocity, just the derivative of x with respect to time, and it's the slope xt diagram. And so I should show you by the graph. Okay, let's switch to the graph. Okay, let me show you. Okay, so here is the xt diagram, and then the green line is position x and its function of t. Okay, you can also think it's a trajectory. Okay, it's a trajectory. Okay, and so we've picked up 2 points, t1 and 2 time. Okay, t1 and t2, and t1 corresponding to x1 and t2 corresponds to x2, and then we can calculate average velocity delta x over delta t. Average velocity delta x over delta t. Okay, delta x divided by delta t. Okay, so if delta t, if we keep changing, if we let delta t approach to zero, like the right hand side, as the time interval gets shorter and shorter, this I think this is the first one is here, or I should use another color. Okay, the first one is here. just like left hand side. And then we shorten the delta t. Here, the second one here, and the third one we keep shorten the delta t. Okay. As the time interval gets shorter, average velocity approaches to instantaneous velocity at t1. Okay, at t1. So if delta t really goes to 0, that means this tangent line or this slope. Okay, this slope. If delta t really approach 0, that's this line. I should draw this. Sorry, not here. Here. Sorry, it's not very straight. Okay, this is instantaneous velocity at t1. Okay, is the slope at this point, at t1 point, or you can say the slope at the slope of p at the t1 point, at the t1. Okay, so if the instantaneous velocity at t2 is the slope here, I don't want to draw it again because this is already a little messy here. Okay, this here, it's here. Okay, that's the instantaneous velocity at t2 here. The slope at the or you can say tangent at the t2. Okay. Okay, so that's the definition of instantaneous velocity. It's just the derivative of position with respect to time. Okay, so and then we go to further. So let me show you some example. Okay, example is very simple example. For example, this one. Okay, the members of highway patrol are more interested in your average velocity or instantaneous versus actual drive. Yeah, I think answer is very easy. Instantaneous speed as you drive. Okay, and so okay, let's see another example in the textbook. In the textbook, it shows you the 4 different trajectory, and or you can say all 4 xt diagram. And then from this trajectory, could you make some comment of this motion? For example, which motion is speed up, which motion is speed down, and which is constant velocity motion, and which one is reverse motion? Can you judge them by the xt diagram? Okay, that's from the rightist one. Okay, the rightist one, you see the curve is going up, and what's the velocity changes? What's the variation of velocity? Okay, and like I said, velocity is slope. Okay, the velocity is slope. So let's draw some slope here. Okay, the first slope is here. Okay, the second slope another time is here. Okay, the other slope is here. Okay. Okay, you see the slope. You say the slope increase as a function of time. A function of time. So that means, so the slope of xt diagram is velocity. So that means it's speed. So this is speed up. When it's speeding up or speed up, or whatever. Okay, so let's look at C. Okay, same analysis. So we just draw a different slope. Okay, the first slope is here. Okay, another slope is here, and another slope is here. Okay, you see the slope decrease. The slope decrease as a function of time. And the slope of the xt diagram is velocity. So the velocity is decrease. So let's speed down. Okay. Okay, and the B. Let's look at the B. Okay, you see the slope. Oh, it's straight line. In a straight line, you see the straight line. You see straight line. Slope is constant. It's constant. Okay, so slope is constant on xt diagram. That means velocity is constant velocity. Velocity is constant, so it's constant velocity. And the leftist example, okay, let's see. Okay, what happened on this motion? That's pretty interesting. Okay, the slope, we draw the slope here. Okay, here. It's how to draw it. Okay, the first slope is here, and the second slope I think is decreased a little bit. Okay, at this point, and then at this point the slope is like this. Okay, so let's make a marker here. Make a little marker. This point here, and point here. Okay, you see the slope is getting decreased. Slope is decreased. So I think before or the left hand side of the dashed line, velocity decrease. Okay, decrease, decrease. And okay, so on the right hand side, what's happening? On the right hand side, what's happening? Let's see. The slope. Let's see. The slope is how to say? Can I say the slope increase? Okay. What happened? How to describe this part correctly? Okay. Be careful for this. I think okay. This how to describe this after the right hand side of the dash line, the motion at the right hand side of the dash line. Let's say. So compared to the middle point, yeah, the slope increase. I should say the magnitude of slope increase. Magnitude. I address this point. I stress this point. Magnitude of slope increase. But the slope is become negative. But the slope is become more negative. Slope is becoming more negative. What does this mean? Okay, the slope is getting more negative, and it's and the magnitude of slope will increase. So I think the best description is reverse direction. It's reverse direction because the slope is negative. Yeah, the slope is negative. Okay, so let's means reverse delta x. Yeah, reverse direction. I'm afraid I'm teaching wrong. Okay, reverse direction, and the speed increase. I think speed increase, but in reverse direction. Speed increase, but in reverse. I say velocity increase. I should say speed increase, but in reverse direction. Okay, that's more correct description. Okay, I think this is it's just like it's a toss up. You toss up something. The object velocity again decrease and then reach to 0 and then go down, and it's increase. The speed increase, but it's in reverse direction. Okay, just opposite when you toss up. Okay, so that's the instantaneous velocity. It's just the position. Make a derivative of position with respect to the time, and the physical meaning is slope of the xt diagram. Okay, and for the next part, I will give you we will do some example question on instantaneous velocity, and we have to use a little bit calculus. In this class I will use a little calculus, okay, and very easy calculus, and I will show you a very easy calculus. I won't use very hard calculus in this class because at the same time you are learning calculus. Okay, so in next video I will show you the example, instantaneous example. And so see you next video. Okay, bye bye, bye bye, bye bye. Okay, bye bye. Yeah. To stop, please.